last class we studied the finite element analysis of transverse vibration of beam, and we developed the elemental equation for the mass, stiffness and force vector. And this particular development of the elemental equation, for that we used Galerichan method, and there is another method which is called Rayleigh-Ritz method. That method can be used for development of the similar elemental equation. So, for brevity we are not covering that method. Now, in the present lecture we will try to see the application of the finite element which we have developed earlier, how we can able to use that for different end conditions or for a system. And for that, initially we will be taking one simple example of simply supported beam, and we will try to find out the natural frequency of a simply supported beam, and even corresponding mode shapes will plot, and will show the detailed procedure how it can be obtained. Even for a rotor system, will formulate using finite element method the procedure how to get the unbalanced response if a particular disk is having some unbalance in the rotor system. And then we will see some other techniques, especially some kind of condensation schemes. If the element numbers are very high, then how we can able to reduce the system equation of motion so that the computation time is less. So, let us take one example of a simply supported beam. So, we are considering one simply supported beam. This is the support of the beam. Now, the property of the beam is diameter of the shaft is, let us say, 10 mm. The length, total length of the beam is 3 meter. Young's modulus of the beam material is this much. Density is of steel, and so with the help of this we can able to calculate the second moment of area. That comes out to be this much. Area of the cross section of the beam would be this much. And now we want to discretize the beam into various number of elements, and for that for simplicity of illustration we will divide this element into 3 numbers. So, let us see equal number of the size of the length of the element are same, 1 meter. 1 meter. So, there are 3 elements, 1, 2 and 3. We can able to give them node numbers also, 1, 2, 3, and this is the 4th node. So, now we will be writing the elemental equation for each of these elements one by one. This is the finite element equation for element 1. In this we have first the mass matrix, which is 4 by 4 size. In this we are, instead of variable we are keeping all the value of the variable. because this matrix is symmetric, so I am not writing the full matrix. And here we have the acceleration vector, which is given as W1 double dot. There is a time derivative, then W1 double dot prime. Prime represent the derivative with respect to spatial, that is a x variable, and this is for W2, and this is W2 prime double dot. Prime represent the slope. So this is the mass matrix. Similarly, the stiffness matrix will take this form. This is also 4 by 4 matrix. This matrix is also symmetric, and here the displacement and slope vector are there for node 1 and node 2, because element 1 is having node 1 and node 2. So corresponding displacement and slopes are having subscript 1 and 2. Then in the right hand side we have the shear force and bending moment. There is the reaction forces and moments. So this is the elemental equation for the first element. Now we will be writing the elemental equation for second element, element 2. So in this, again I am giving the detailed steps so that the procedure is clear. This is the mass matrix. This is because the element size is same and dimensions of the element is also same, so we are having this mass matrix identical to the previous one. If there is a step change in the diameter of the shaft, then maybe we will be having changes, especially in these terms, because they contain the dimensions of the shaft. Here again we will be having some changes, because now the element 2 contains node 2 and node 3 in left and right side of the element 2. So we have W2, W2 prime, W3, W3 prime, and these are accelerations, so double dot terms will be there. Then comes the stiffness matrix. Here is similar to the previous element, element 1, because this element is of the same geometry, same material property as the previous one, so they remain the same. This again both are symmetric. Here we have displacement and slope vectors at node 2 and node 3. Then in the right hand side, because we are considering only the free vibration, so there is no external forces and moments, only internal forces and moments are there. So here correspondingly we will be having subscript 2 and 3 in the shear force and moments. So now I have shown how the two element equations, one element is still remaining, so for completeness I am showing that also. So this is the element 3. In this I am just showing the mass matrix, which is exactly same as the previous one. Whatever the changes are there I am mentioning here. So here, since element 3 is having a node 3 and 4, so the subscripts will be accordingly changing to 3 and 4. This is the mass matrix. Stiffness matrix is also same, because the dimension and the material property of the element is same as the previous ones, only these subscript will change to 3 and 4 corresponding to the displacement and the slope, and in the right hand side again there will be shear force corresponding to node 3 and node 4. So these are the three elemental equation which we have illustrated, because now we want to get the system equation. So we need to assemble all these three elements. So now I will be showing the assembly procedure, how we will be assembling these three elements to get the system equation. Because this is a big matrix, so I will be showing one matrix in this particular slide, the mass matrix, and similarly I will be showing the stiffness in the next slide. So here we have 1.46 into 10 raised to minus 3 coefficient, which is common. Then we have 156, 22. These entries are coming from the first element. If you see previous mass matrix for element 1, these are the entries in that. So this is coming from the element 1. Now for element 2 we can use a different color, 156 plus 22, 54 minus 13 plus 4, 13 minus 3. This is red color entries are coming from the element 2. If we want to see how they are coming here, let us first write the vectors. So here W1 double prime double dot is there, then we have W1 double dot prime, W2 double dot prime is not there here, then W2 double dot prime, W3 double dot, W3 double dot prime, W4 double dot, W4 double dot prime. So you can see that the first 4 entries in this vector is corresponding to element 1, and the element 2 contains the node 2 also. So there will be overlapping when we will assemble the element 1 and 2, there will be overlapping of the element 1 and element 1 mass matrix, especially at node 2, which is common to both element 1 and 2. So these are the overlapping terms we can able to see. Next we will be entering the mass matrix for the third element. So third element is having common node 3, which is there for node 2 also and node 3 also. If you see here, this element 3, node 2 and 3, this element 2. So element 2, sorry, this is 3 and this is 4. So element 2 and 3 is having 3 as common node. So we are getting this overlapping of the terms of the mass matrix. So here it will be 54 and then last term will be 13, then here it is 4, 13 minus 3, here 156 minus 22, and last one is 4. So you can see that now the size of this matrix is 8 into 8. Earlier it was individual, it was 4 into 4, now it has become 8 into 8. Similar assembly we will be doing for the stiffness matrix. Now I am showing the stiffness matrix. So these are the entries from the first element. And we have this vector W1, W1 prime, W2, W2, W2 prime, W3, W3 prime, W4 and W4 prime. For second element we can use a different color. So in this we will be adding 12 plus 12 plus minus 6 plus 6 plus 4 plus 4 minus 12. These are coming from the second element. These are coming from the second element. Now for the third element, again we 12 plus 12 plus 6. There is one term missing here of the second element, this. So here we have two more entries, one is minus 12, another is 6. So this plus 4 minus 6 and 2, then below this 12 is there, minus 6 and 4. So you can see that these black entries are coming from the element 3, and rest of the terms here they are 0. In previous mass matrix also the rest of the terms are 0. So all these are 0. Here also we have all the terms 0. Here also. So this is the stiffness matrix, and previous was the mass matrix. This is equal to the internal forces, that is minus S1 M1, then S2 M2. This is coming from the first element. From second element, these are the entries. This is S3 M3. Then from the fourth element, again we have this is minus S3, this is minus M3, S4 M4. So you can see that these terms are becoming 0. So whatever the reaction forces were acting at nodes in various elements, once we join them, obviously they will cancel each other. So because of that they are becoming 0. At these two locations and here, which are the shaft ends, there because it is supported through that is simply supports are there. So this will be having shear force and bending moment. It depends upon the end condition, because while development of the element we don't consider the boundary condition. So now we assembled all the three elements. Now need is to find out what are the boundary condition and apply suitably. So let us see now the boundary conditions. This was the node 1, 2, 3 and 4. So displacement, because this is simply supported end, so displacement here it is 0, and bending moment is 0. Here this is also simply supported, so here W4 displacement is 0, and bending moment is also 0. Because this is simply supported end, so we will not be having the shear force 0 and the slope will also be having some finite value, but for other kind of end conditions we will be having different boundary conditions. So these are the boundary conditions we need to apply to the our equation, assembled equation. So let us see where we will be substituting these values. So this is the mass matrix. So here we can see that W1 is 0 and W4 is 0. Similarly, in the stiffness matrix we have these conditions, and in the internal force this M1 is 0 and M4 is 0. So in this particular equation, in the right hand side, the equation is having this form. I will just write in the compact form: M W double dot plus K W is equal to the internal forces. So in this particular right hand side, you can see that this term is there, in which S4 is non-zero and S1 is non-zero. So and all other entries are 0. And if you go back to the previous slide, you can see that W1 is 0. So when we multiply this vector with the matrix K, this whole column will be getting multiplied by the 0. So it will not contribute anything. Similarly, this one W4 is 0. So last but one column will not contribute anything because they are getting multiplied by 0. So we need to eliminate them. Even the first row also we need to eliminate, because in this S1 is unknown, so we are eliminating them. Also last but one row we need to eliminate. Similarly, in the mass matrix, on the same lines we can eliminate these two columns, the first column and the seventh column, and the first row and the seventh row. So whatever remaining terms are there, that will be writing separately. That is nothing but the system equation after the application of the boundary conditions. So that will be having a reduced form, and it will take this form. This is the mass matrix. So we eliminated the first row and seventh row, and similarly these columns. So we got these numbers. Also, whatever the contribution from various elements was coming at the common node, that we are adding up and showing here as the resultant numbers. So you can see that now the equation has reduced from 8 by 8 to 6 by 6, and here we have vector corresponding to W double prime 1. So W1 is not here because we have eliminated them, because its value is 0. Then W2 double dot is there, W2 prime double dot is there, W3 double dot is there, W3 double dot prime is there, W4 is not there, and W4 double dot prime is there. So this prime represents slope, as I already told. The rest of the terms here they are 0. These are all 0. Similarly, this side also. Here also all terms are 0. So, this is the reduced form of the mass matrix. Similarly, we will be having stiffness matrix, that is the stiffness, reduced stiffness matrix. So, I am writing by elimination of the first row and 7th row, and we are adding all the terms which had from various elements. So, this is also obviously 6 by 6 matrix. Remaining terms are 0, and here also, as in the mass matrix, we have W1 prime, W2, W2 prime, W3, W3 prime, and W4 prime. W4 is not there because its value is 0, and toward the right side we have a vector contains 6 terms, all 0. They are corresponding to the shear force and bending moment, which are either got cancelled at the intermediate nodes. So, this is a transpose of the vector. So, this particular matrix which we obtained is of this form. This is a standard form of the governing equation of a dynamic system. So, once we have the system equation in this form, now we can able to analyze for the free vibration, because in this case we have not considered any external force. So, now we will be solving the free vibration analysis of this. So, for that, if we are assuming the displacement vector as some amplitude, and let us say omega is the natural frequency of the system. If we differentiate this twice, we will get j omega square e j omega t, because this is independent of time. And if we substitute this in this equation, governing equation, we will get minus omega square m plus k, and w bar, which is amplitude, will be common. This is equal to 0. So, this is a standard eigenvalue problem. And we can get the eigenvalues of this system in two forms. Let us see what are those two forms. So, if we, in the previous equation, if we multiply the whole terms by k inverse, we will get k inverse m minus k inverse. So, I have taken omega this side. Omega is nothing but natural frequency, this is square of this. So, if we obtain the eigenvalue of this, let us say this is a matrix. So, inverse of that and square root will give us the natural frequency. So, whatever the eigenvalue we will be getting from here, we have to do the inverse of that and then take the square root, that will be the natural frequency of the system. Sometimes the stiffness matrix is singular, then what happens, we cannot able to invert the stiffness matrix. Then other form of this is, we in the previous equation we can see that instead of multiplying by the inverse of k, we can do the inverse of m. So in that case, we will be having the following form of the, this is m inverse k. So this is also a standard eigenvalue problem, and if this is a B matrix, eigenvalue of that, whatever we will get, if we take the square root of that, that will be the natural frequency of the system. Now, once we obtain the natural frequency of the system, there are corresponding mode shapes are also present. So what we need to do, once we obtain, let us say, n number of natural frequency of a particular system, so one of the natural frequency will choose first, and we will be going back to the previous equations, these equations, in which this particular equation we will be substituting the natural frequency which we obtained here, and with the help of this we will get the relative displacements. This is the displacement vector. So relative displacement of various nodes will be getting it, and that is nothing but the mode shape or the eigenvector of the system. And for each natural frequency we will be having a unique, or I should say a one set of eigenvector. All are relative, because maybe one of the eigenvector value we have to choose, and remaining will be normalized accordingly. So for every natural frequency we will be having a mode shape. And now we will see for the problem which we are tackling, how we can able to get the various natural frequency, and also we will see the convergence. As we will increase the number of element, how the value of the natural frequency it converges to the actual value. So now I am because these eigenvalue problem can be solved using MATLAB very easily. So now I am directly giving the eigenvalue for various number of elements, because here we are shown for 3 elements, but we can able to easily increase the number of element with the procedure we have shown. I am showing the natural frequency comparison for, let us say, mode 1, mode 2 and mode 3. The exact solution that I will be giving the expression of that. So let us say first is the finite element method with 3 element. We got 14.19 radian per second, all unit is radian per second. First mode natural frequency, second mode is 57.39, and third is 141.6. and if we increase the element to 6, it gives us 14.18, 56.77, 128.1, and for 100 element I am increasing suddenly, because once we have the program for the assembly procedure, number of element is not a problem, 14.18. So hardly any improvement with the increase in the element for the first one. Second one slightly improved, third one there is some improvement, but now it is quite close to the previous one. And if we see the exact formulation, natural frequency for simply supported beam is given as n square pi square E I by m L4, where n is the mode number 1, 2, 3, and we have m as the mass per unit length rho a, and here E and other things we already mentioned previously. So, if we substitute this value here, we will get 14.18 n square. N is the mode number. So, for n is equal to 1, that is it, with the 6 element we are getting quite close to the closed form solution. So, closed form solution I am writing here, that is exact is 14.18 for node 1 mode 1, and for mode 2 it is 50, for mode 2 it is 56.12, and for third mode it is 127.6. So, you can see that when we took 3 element, the first natural frequency was quite close to the exact one, second was marginally okay, but third one there was large difference, but with the 6 element we could able to reach quite close to this, and there is marginal improvement with the number of elements. So, even the 6 element is quite accurate for this particular case. Now, we will see how to extract the eigenvector from eigenvector, or the mode shape from the eigenvector, because for if we are using a MATLAB, corresponding to each natural frequency or the eigenvalue, there will be a eigenvector, and I am just showing for 3 element case how the for corresponding to the first natural frequency eigenvector look like, and then how to extract the mode shape from that. We had the for 3 element, these were the displacement and slopes after applying the boundary conditions. That was the 6 by 6 matrix, and the vector was 6 into 1. So, the first column of the eigenvector matrix, which we get from the standard eigenvalue routines, subroutines, you will find these kind of numbers. First column will be having 6 entries if we are using 3 element, and these entries are in the number form, but we have to interpret them. What are they? This is positive. So, you can see that whatever the vector we had, so they are indicating what are the values we have, and for mode shapes we know that we need the displacement, and W1 we already know that because of this simply supported end condition they are 0, and W4 is also 0. So, basically we extracted the mode shape, which is the displacements is minus 0.42, minus 0.42 and 0. So, if we want to plot them, this node 1, 2, 3, 4. So, you can see that because negative sign, if we ignore, these two are 0.42, 0.42, these are 0. So, this is something, if we join them by quadratic or the cubic curve, the shape function will be getting this kind of curve, which is nothing but half sine wave, and we know that a simply supported beam, the first mode is half sine wave. So, similarly we can go for the second column, and we can extract the mode shape corresponding to the second natural frequency, and similarly for the third and fourth and so on. So, these extraction of the mode shape up to various modes I will be showing in the a plot form. So, this is the mode shape of a particular different beam having I think I will again repeat this. So now I will be showing the mode shape for simply supported beam for various number of modes. So this is a mode shape plot which shows up to 5th mode for simply supported beam. So you can see that with a line with circle is this representing the first mode, and there are various other modes. Second mode is by the star. So this is the second mode in which the full sine wave is there. First mode was the half sine wave, but this is the full sine wave. Similarly, we can able to see the third, fourth and fifth. So we have already seen how we can able to obtain the natural frequency and mode shape for a particular beam when it is undergoing transverse vibration. Now we will see another example in which the similar simply supported a shaft is there, is carrying a disc, and it is having some unbalance. How we can able to obtain the unbalanced response, and because the response or displacement of a rotor is a vector quantity, so it will be having magnitude and phase. So this is the aim of this particular example. So let us start with the diagram of the particular shaft, which is simply supported at ends. The dimension of this is exactly same as the previous example in which we had 3 meter beam. Only difference here is here also I am dividing this into 3 element, but we are keeping a disc at the third element, and this disc is having mass of 1.5 kg. It is having unbalanced mass of 0.005 kg at the radius of 0.05 meter, and the phase of that with respect to some reference point on the shaft is 30 degree, and here we have the phase something like this, in which let us say this is the y axis, this is the z axis, unbalance of the shaft is here. So this is the phase with respect to, so we are measuring the phase with respect to horizontal axis y. So now we have described the problem. Now we need to develop the elemental equation for 3 element. Slight difference will be there in this present case as compared to the previous one, because one thing is there that now because of unbalanced force, the motion of the beam or the shaft in horizontal plane and the vertical planes are now coupled. That means we need to consider the equation of motion of horizontal plane and vertical plane together. In the previous free vibration analysis, we considered the one plane motion only. So for that, let us see the elemental equations and how we can able to get the unbalanced response from that. So this is the elemental equation of element 1, and here we have considered both the plane motion. So you can able to see that here we have the displacement slope in one plane, then in the same plane of the same node, because node 1 now has 2 displacement, one in horizontal direction, another in the vertical direction, similarly slope, and similarly at the node 2 will be having 4 coordinates, 2 for linear displacement and 2 for the angular displacement, and this is the rearrangement when we assemble the two plane motion. They are coming from the elemental equation. This for the mass matrix, and this is the stiffness matrix, and here this is the external force which is 0, because on element 1 there is no eccentricity. We consider the eccentricity in the disk only, which is we are assuming to be at element 3. These are the internal forces. And for the second element, because we are considering the disk in the third element, so second element will remain same as the element 1. Only thing, in place of node 1 and 2, in element 2 the node numbers will be 2 and 3, but the form of the mass matrix and the stiffness matrix will remain same, but there will be change in the third element. So let us see how the third element take the form. So this is the finite element equation for the third element, and you can able to see that there is a contribution of the disk mass which is coming here and here, corresponding to the displacement in node 3 and in the horizontal and vertical directions. So they are corresponding to these. So 1.5 was the mass of the disk, and because this is common here, this term, so we need to divide that by that amount. So this is the contribution of the disk. Stiffness matrix is not getting changed because disk is not affecting the stiffness. External force is getting changed because now this represents the unbalanced mass. So this is and where omega is the spin speed of the shaft, and this particular quantity is j theta. Theta is phase, so this term comes from the phase term, and you can see that the force in y direction, which is this one, and force in the z direction, which is here, if rotor is rotating counterclockwise direction, so z will be lagging by 90 degree with respect to y. So we will be having relationship between the Fz is equal to minus j Fy, because minus j represent the phase difference between the y, Fy and Fz is 90 degree, and Fz is lagging Fy by 90 degree. So the same thing is appearing here. We are multiplying by minus j because this is the Fz force which is lagging Fy by 90 degree. This is the internal forces corresponding to node 3 and 4. So now we have obtained the we assembled the we have obtained the elemental again. Now we have obtained the elemental equation of all the three elements. Now we need to assemble them and apply the boundary condition so that we can get the system equation from where we can obtain the unbalanced response. So this is a mass matrix of the assembled equation, in which we have all the three element equations combined, including the disk also. So next is the stiffness matrix. This stiffness matrix is also of all the three elements, and this is the total external force vector, and these are the internal forces. You can see that the internal forces at the common nodes will be becoming 0. Now we will be applying the boundary conditions. We know that what are the boundary conditions we have. That is, at node 1 we have W1 and V1 0, and at last node we have both the displacement in the horizontal and vertical direction 0. Similarly, moments in the two directions at node 1 is 0 and in node 4 is also 0. So, if we apply these boundary conditions here, this is the reduced form of the equation. Once we apply the boundary condition, the system equation will get reduced. I am showing only the stiffness matrix, how it looks like. So, this is the stiffness matrix in the reduced form. Similarly, we can have the reduction in the mass matrix. This is the external force. All the internal forces we are keeping 0 here. All other non-zero internal forces, those equations we eliminated as in the previous case. So, once we apply the boundary condition, the assembled matrix will reduce to a smaller matrix. In this particular case, because we have these boundary conditions, you can able to see that correspondingly we will be having only these second, 4, 5, 6 and 7, 8 up to 12, 14 and 16 columns and rows will be retaining, others will eliminate, because if you see this particular stiffness matrix is having 16 into 16 size and we are eliminating 4. So, there will be total 12 into 12 matrix of the mass and stiffness will remain and others will be getting eliminated. So, what we can do, I am just showing the one of the stiff matrix, that is the stiffness matrix. The size of this matrix is 12 into 12. We are already eliminated those rows and columns which are giving us no contribution because of they are getting multiplied by 0, and in this case here you can see these forces are acting at node 3 and both in the horizontal and vertical direction. And now this particular equation is in this form, compact form, which is standard dynamic equation, and it contains the force also. In previous case only free vibration was there, so this force term was not there. Now again we can take the solution of this as amplitude and a harmonic function, which is omega is nothing but spin speed of the shaft. So, if we differentiate this twice, we will get minus omega square w e j omega t, and if we substitute these two in the equation of motion here and here, we will get minus omega square w so we will get minus omega square m plus k matrix. W bar is common, which is amplitude, and we have the force again we are writing as amplitude, because the force can be written as, this can be written as j omega t, because this is coming from the unbalance, and correspondingly we are choosing the response of the same frequency, and whatever the phase information, because for the present case there is no damping, so the phase between the force and the displacement will be same, but in case there is a damping, then the phase information will be contained in this and it will be then complex in nature, but at present because there is no damping, so it will remain real. Now this particular matrix, we can able to call this as A matrix. So we can write this as A, which is function of speed W bar is equal to F bar. Now to get the response, we need to invert the A matrix. A matrix okay. So once we got this, here you can see that omega is the variable. So omega can be changed from 0 up to some omega max. So one by one we need to change omega. If we take omega is equal to, let us say, 100 rpm, we substitute on this, and then we know the force, we can get the response for that omega, and let us say 100 rpm. Then we can change this. Again we have to obtain the response corresponding to this separately by different run, and so on. We can get the these W bars for various value of omega, the spin speed. Today we have seen how to the application of the finite element method for finding the natural frequency and mode shape of a simply supported beam. In this example, we have taken only 3 elements of the beam, and we showed how to write the elemental equation and then how to assemble those equations, and then after getting the assembled equation, the application of the boundary condition, and how to get the reduced form of the system equation, which can be used for obtaining the natural frequency and mode shape. Subsequently, we applied the finite element method for finding the unbalanced response of a rotor system in which there was one disk having some eccentricity, and through detailed steps we showed how the unbalanced response can be obtained for the rotor system.